Okay, I think we'll get started. So today we're going to do a lab that involves talking through the serial port to our PIC10F200. And this is a really cool lab. It's a nice utility build to have. And actually I use it in our research. And so I'll show a couple of pictures from the research lab where, although it wouldn't technically be necessary, it's a really handy thing to have. And so basically what we're going to be able to do is just send a impulse, whether usually just a keyboard hit, from the computer to the PIC via the COM port through UART, or Universal Asynchronous Receiver-Transmitter protocol, which is a serial communication. And you communicate using the serial port. So we'll just use PuTTY, a terminal for Windows or Unix. I think Mac has its own terminal program, but just to send a character. We'll see that this then can function as a computer-controlled switch. We're going to just turn on and off an LED, but in the lab, I actually use it to turn it on and off a MOSFET that then acts as a switch for a much higher voltage shutter, optical shutter, for some of the laser work that we do. And that's driven by a solenoid, so it needs 26 volts and 250 milliamps, so well beyond what the PIC can provide, but certainly definitely within the what a MOSFET transistor can apply. And so using these in tandem has been very helpful for me. Now, we're not going to get, this project is not going to get deep into these ideas. We have another project that will look at this more closely. All we're going to use is just the initial signal that something's coming from the computer, and that's going to launch our PIC10F200 into a toggle mode. So it's just going to change the state of the output pin GP0 from high to low, if it was originally high, or low to high. So it'll just kind of be just like a light switch that we can control through the serial port. So we will not actually be reading data as it comes in, which is really what, when we get into more of the details of this, will be important. All right, so essentially with the UART communication, you have a USB plug into your computer, and then you have some sort of UART device, and well, I'll talk about 3 of them here in this. And in all cases, the data signal is held high, and then it's active low, so it drops down low to send data. The basic structure is it's high, then comes a start bit, then 8 bits of data. This could represent an ASCII character, for example, and then a stop bit. Now what we're going to do is only read off of this start bit, and we're not going to care about what happens afterwards. So again, we're not getting into the details of how do you read each of these individual bits as they come through. That's going to be much more of a timing thing. All we have to do is make sure that we let all of this pass before we pull the input again. All right, so let's see what this looks like on the board and in the code and so on. So right now, we can see the PIC controller here. These wires, again, are just to be able to program it with the PIC-Kit5. We have a simple output to a LED, but as I say, this output could go and drive a MOSFET transistor as a switch if you need to drive a higher load object. Then we have the input, and actually the input and output pins of the UART, so the transmit and the receive. The reason we loop that around is so that when we are sending a character, it will also send it back to the terminal, so we'll see that the character was sent. Although not necessary, you could just let that receiver bit dangle or ground it or whatever you want to do. All right, so this is the particular UART device that we're using, and I'll show you what that one is. That is, I got this on Amazon, $10 only. I never did get it to work with Windows 10, but it works automatically with Windows 11. And we can see here on the device manager, move the device manager up here. And here are our COM ports. And this is it, COM port 4. So if I pull this out, we lose that device, and then I'll plug it back in and it'll pop back in. So we are COM port 4. Now if we want to talk to this, we can use, well, let me first show some of the others that have also worked for me. This is the FT232H, and this can send UART, also a bunch of others, other protocols, and this has worked as well. Again, fairly cheap. There was some drivers that I needed to install for Windows 10, but on Windows 11 and on Unix, I should have said on this one as well, Unix, it just works right away, so it recognizes it. And then finally, this is what I actually use in the lab. This is a nice convenient thing that just has its own cable that gets connected right to the computer. And again, Windows 10, Windows 11, and Linux just recognized it right away. So this is a nice one. It also comes in, this is 5 volts, but I also have it in 3.3 volts in case I needed anything to talk to a like a Pico or something like that. So these are 3 that I've used, and they work well for the UART communication. All right, let's try to run this, so I will open up PuTTY here, and what we're going to want to do is choose serial, and then I'm going to choose COM 4. And I'm going to speed this up a bit. So I'm going to increase the baud rate considerably, and then open up a terminal. And now what we should see is when I press a character, it toggles. Doesn't matter what character I press. When I press a keyboard character, that gets sent to COM 4 via the PuTTY program here, and then gets sent as a 5-volt signal to the input of the PIC10F200, and that's just polling that GP1. It's just polling that for a low. So it's looking for it to, it's high, it just goes in a loop. As soon as it goes low, it comes out of the loop and then goes to a function that will turn on or off the light. Okay. Now let's go look at the code, and then we'll come back to this again here. So yes, I'll close that session. Let's look at the code here. And, oops, I guess this is a practice program to UART toggle. Make sure I have the right one here. Yeah. And this is all the stuff that's always there, turning off the watchdog timer, etc., adding the include file, setting the program counter to start at main. Main here, again, as we've set up for this series, we are using this binary literal to then get written to the tris register, and this, the last 4 digits here, determine whether the pins are inputs or outputs. And then finally this one ensures that GP2 is acting as an input rather than an external clock. And that writes to the option register. The main action here is in the main loop, and we have 2 loops here. And so what's going to happen is we'll enter the main loop, and we will set the output to 0. So this will just be an automatic starting state of the toggle switch. Then we will call hold loop. So we're calling the function hold loop. And what hold loop does is it is essentially just polling GP1. And so we know that GP1 is normally high. So when nothing is coming from the computer, the signal is high. So we'll skip if clear. Well, it's not clear. It's high, so we go to hold loop and we just spin in this loop. As soon as the signal comes, so as soon as the start bit comes, and then of course all the other signals, but as soon as the start bit comes, we are going to clear. This will be set low. And so then that will jump out of this, jump over this loop and come out of the function. And once we come out of the function, we're going to put in a small delay, and this is critical because we don't want to sample we don't want to run through this so fast that we sample the tail end of the signal that just came. And we're actually going to see this happen and see what happens when that happens. So we put in a little bit of a delay, and so just using our delay functions from before, and just a short delay, several not even a millisecond, and then we set pin high, okay, and then we go into hold loop, and hold loop again is waiting for another signal. So we've put enough delay in here that that first signal has passed. So if I press the letter D or the space, that whole 10 bits of information comes across and is long gone by the time we get back to hold loop. So it's sitting there high again, and it's skipping in the loop until we get another low. So we get another low. I hit the keyboard again, and now we are down in this hold loop. We add a delay, and again, to clear, we go back to main loop, and so we loop back up here. That sets the bit low, so it toggles it low. And so essentially we have two regions here, and the hold loops are just spinning there until we get another signal. So it'll hold the system in a high state, hold the system in a low state. And we found this has worked really well. We've been using this in our setup in the lab for 6 months, and have never had any issues with the toggle switch working. We did have one of the PIC10F200s fry for some reason. I think we had a little voltage spike, so I think they're pretty sensitive to that. But just replacing it with another, and of course these are just 80 cents, so it's not a catastrophe in the lab if one of these goes. So this is a very handy loop that we've used in the lab. Let me show you some pictures from the lab. And this is I do some optical spectroscopy, and I'll probably have some other videos on that. But in terms of what we're interested in, sits right here, and so we have a computer talking to this. Now, technically, we wouldn't need this at all because we're using a Raspberry Pi as a computer, but we wouldn't need to. We could use a different computer, and the Raspberry Pi, of course, has a lot of outputs that we could just use and not have to have this additional step. But we had this around, and this is very convenient for us. And so it's sitting right here, and what we can see is there's some power coming in, 5-volt power to power the PIC, and then 26 volts that are across the MOSFET, and I'll get a closer picture of that here. So here we are. Again, here's our breadboard. Here's the MOSFET, and then here's the PIC. We can see these cords going out to this shutter. So this is a shutter. The laser's right here. The laser will be on, and the sample's down here. And this is a cooling jacket for the sample. And so we want to send the light into the sample, but we want to control when that happens. So we have the computer tell the shutter to open. This is a solenoid sitting right here, and that will pull that shutter open when it has 26 volts applied, and then close it when it has 0 volts applied. And so we have another power supply, actually it's sitting right here, that we would plug in. That's a 26 volt power supply that'll run the solenoid. And so that way we can control when we have the light on the sample and when we don't. And so this is an application of this for us that we've been using, like I say, for a long time now in the lab. All right, well, let's get to let's just look at a few other details. First, let's just leave things the way they are, and I'll go back to PuTTY, and I'll call serial 4, but I'll leave the baud rate low. And what we're going to see here is that we clip the tail end of the signal that comes through, and we don't get the behavior that we want. So nothing has changed here other than the baud rate is slower. So the 1s and 0s are coming slower, and each bit is on for a longer duration. So let's go ahead and open that up, and I can type, but you can see I'm not getting the type of results. Like F, it works with F but doesn't work with D, and that has to do with when are these being sampled. And the PIC is going through its whole cycle and coming back before the string of bits are gone. So what we can do, let's close the session. Let's go ahead and increase this. Let's just try 20 here. So we'll increase the delays and try to run. And then I'll open up PuTTY again. Serial COM port 4, and I'll stay with this baud rate. And now that we have a longer delay, that should clear and things should work then. So let's try that. And I'll hit D, J. Everything is working as planned, but now at a slower baud rate. And for our purposes in the lab, I think we do have it at 90. I guess I can't remember for sure, but we have a slower baud rate. It doesn't matter that much. But if you needed a faster timing, then you would increase the baud rate, and you can shorten down that delay. All right, so this is a good example of a very easy program to write in terms of the code, but it's a helpful one in that it acts as a very nice toggle that the computer can use, and so you can write code to send out. So yeah, we used PuTTY, but you can easily write a Python program to talk to the serial ports. That's all. ChatGPT will just write that for you, for example, and so you can do that very readily and build it right into your program. So let me see if maybe I don't have that in here. Oh yeah, so on the screen here, and we have a little ability to control our experiment. So in Python, I've just written essentially a GUI that looks like a regular window, and within that, it calls a function that is essentially this function in the code that sends a signal, and that's just part of the protocol when the whole system runs to collect our data in our optical experiments. All right, so that is about it, and so hopefully you can use this project in your own work.